Next up is Konstantinos Mamis. Please.
Thanks a lot. So these are our first results from our project on quantifying the effect of early stage cancer on the cell-free DNA levels in the blood. This is a project that started when I was a postdoc in the University of Washington under the supervision of Professor Ivana Bozic, and it's also continued from my new position. First of all, as we all know, the survival prognosis when cancer is detected early on, it's much, much better than when cancer is detected in late metastatic cases. So it's really, really important if we can detect cancer early on. However, time and time again, publications have shown that people avoid going through routine cancer screening, especially because of the invasiveness of the screening techniques. So we really want to move towards less invasive and more accessible screening methods. However, there's always the question if these methods are accurate. So a really promising alternative to invasive screening techniques is blood-based screening for cancer. These are much more less invasive, and everyone does once a year some blood work. What we can check in this blood-based cancer screening is for tumor-associated proteins where the levels are increased in the presence of cancer. But we can also check for the cell-free DNA, cfDNA, which is the DNA in blood circulation that's not bound to a particular cell. The existence of cfDNA in the blood has been detected in the 40s. And in the 80s, it was reported that increased cfDNA levels exist in cancer patients, especially in advanced stages. And also, again, in the 80s, there was detected that mutations that are harbored in the cfDNA are also detected in the primary tumor in cancer patients. So this cfDNA is a really promising cancer biomarker for early detection. But while it is really accurate for late stages, we're really interested in what we can say about cfDNA for early cancer detection. However, in early cancer stages, the mechanisms by which cfDNA is shed into the blood circulation, as well as the mechanisms that are clear, that cfDNA is cleared from circulation, are not fully understood. So we would like to contribute towards answering questions like in which and how much does cancer affect the total cfDNA concentration? Is this effect cancer type specific? And does it differ between early cancer stages? And if it's directly related to tumor size? This is actually in conjunction with what has been published recently. There was this recent publication in Cancer Discovery where they've tried to determine the tissue of origin for cell-free DNA. And counterintuitively, it was reported that this increase in cell-free DNA levels in early cancer stages does not originate from the tumor. It's not the tumor that's shedding the increased cfDNA. And they've postulated that the presence of cancer likely results in a systemic cfDNA increase, possibly due to increased shedding from non-tumor tissue or impaired clearance. So we would like to use a bit of math in order to understand better those cfDNA mechanisms. So mainly we will use previously published data from Cohen et al. This is a publication in Science 2018, where a vast data set for healthy individuals and stage 1 to 3 cancer patients has been published. Here we see the probability distribution of cfDNA concentrations in healthy individuals and not metastatic cancer patients. We see, of course, that in cancer patients, we're having this fatter tail towards higher concentrations. However, these two distributions do not differ much. So to base statistical tests on the difference of these two distributions. So what we've done using this data set is, first of all, we did a preliminary statistical analysis. We see no statistical significant difference between sexes or age groups. We also didn't detect any statistically significant differences between stages 1 to 3, except for breast cancer. And by analyzing every cancer type separately, what we find, and that's our main result, is that cancer present leads to a multiplicative increase in cfDNA concentration compared to the healthy individuals. This happens on the distribution level, meaning that the mean cell-free DNA levels are multiplied by this factor, while we're having the same coefficient of variation in both healthy individuals and cancer patients. And we conducted the Kolmogorov-Smirnov tests in order to determine this multiplicative factor value. And this actually is shown in this plot. These are the cancer types that were reported in the Cohen et al. Dataset. And by this blue solid line, we see the cumulative distribution of healthy individuals. This is shifted towards this colored solid lines by a multiplicative factor. And the dashed line is the cumulative distribution from the cancer patient. So we see that the translated solid line and the dashed line actually are in a really good agreement. So this was a really interesting result, and we would like to connect this with the previously published results. And it's also really good, like in order to understand if it's shed from a healthy tissue or from the tumor, it was really important that in the Cohen et al., they've also reported for the concentration of the most prevalent mutation in the blood. And they've also conducted biopsies to the primary tumors, so we can check if the most prevalent mutation in the blood, in the cfDNA, is actually also present in the tumor. So in the cases where this mutation was not present in the tumor, we could safely say that it was shed from healthy tissue. And for this circulating mutant DNA from healthy tissue, we can see comparable multiplicative increases in the distribution between healthy individuals and cancer patients. So this points towards the direction that mainly the increased cell-free DNA is shed from the tumor. Now, this increase from non-tumor tissue could be the result of increased cfDNA shedding, of course, a slower rate of clearance, or a combination of both. So in order to understand this, we use an additional data set that was published in Maddox et al. 2023 in Cancer Discovery, where they also report the tissue of origin of cell-free DNA for healthy patients and with patients with pancreatic and ovarian cancer in early stages. And they were able to report the tissue of origin based on a deconvolution of the cfDNA methylation profile. So there, we see that the most cfDNA in all individuals is shed from leukocytes. The percentage in cancer patients is just a bit less than in healthy individuals. And in this data set, we calculated the correlation between cfDNA concentrations from leukocyte and non-leukocyte sources after we exclude some outliers. And what we found here is that practically there's no correlation between leukocyte and non-leukocyte shed cfDNA in healthy individuals, while there's really high correlation in cancer patients. And this can be shown in this graph here. So we really want to search, we're in search of a model for CFTNA mechanics that can account for the multiplicative increase in the total CFTNA concentration, but it can also account for the increased correlation between leukocyte and non-leukocyte CFTNA levels in cancer patients. First of all, of course, we use just a linear model. Here, S is the shedding rate, E is a linear clearance rate. And we can see that the linear model cannot account for the increase. However, if we use a Michaelis-Menten type of clearance, in order to model the saturation of CFTNA when the total CFTNA levels are increased, this model, the simple model, can account for both the multiplicative increase and the increased correlation between leukocyte and non-leukocyte shed CFTNA. And here, what we did is a preliminary fitting of the model parameters. We were able to fit, first of all, for healthy individuals, the model parameters, in order to have a good agreement between the distributions for total CFTNA, leukocyte CFTNA, and non-leukocyte CFTNA. And we can see for this fitting, the correlation coefficient between leukocyte and non-leukocyte CFTNA is really low, 0.1. And by increasing the shedding in both leukocyte and non-leukocyte sources, we have a good agreement of the distributions for pancreatic cancer patients, and most importantly, the correlation coefficient has increased. So this increase in the correlation can be attributed to a saturation mechanism at play. So I would like to sum up a bit our results so far. The multiplicative increase varies greatly for cancer type to cancer type. The most increase we see is in liver cancer. Counterintuitively, increased CFTNA does not come from tumor, but from healthy tissue. And these increased CFTNA levels can originate from both increased shedding, but also a really pronounced saturation mechanism at play. And the shedding from the non-leukocyte tissue is increased more, as we can see from data in the presence of cancer. This really high increase in the presence of liver cancer could also be related to the fact that CFTNA is mainly cleared from the liver. And some future directions that we are currently actively looking at, we would like to refine our model to account for alteration in CFTNA dynamics happening from pre-malignant stages to cancer. Let's say for liver cancer, the path from cirrhosis to hepatocellular carcinoma. And would like to explore the mechanism that result in this increased shedding. Is the increased shedding a result of impaired ferrocytosis, or is an active CFTNA release mechanism from leukocytes that's at play here? We would like to couple our CFTNA model with a model accounting for the tumor growth. This is really straightforward for later stages in cancer, but we really want to understand if we can do that for earlier stages. And of course, there's always the question of data availability. So we're also working in having access to that. And with this, I would like to thank you for your attention, the opportunity to share this with you, and for any questions.
So I see the questions, but I think could we just move it to the break so that we can all get a quick coffee and get everyone back in here for 5 past. Okay. So thanks everyone for this session. Definitely grab them at the coffee break. I've got questions too. Thanks.